Hello, this is Ms. DB. In this video, we are going to go over the information in 12.6 on tessellations. We will use transformations to draw tessellations and identify regular and semi-regular tessellations and figures that will tessellate. Oops. All right, so a pattern has translation symmetry if it can be translated along a vector so that the image coincides with the pre-image. For example, if you were making a border along a wall and you made a figure, let's say you made a right triangle, and then you picked up that stencil and you slid it along the path and you continued creating right triangles as you went. This is translation symmetry. A frieze pattern is a pattern that has translation symmetry along a line. So this would be an example of a frieze pattern. So here's some examples of frieze patterns. You find these on the borders of rugs, along the top part of buildings often. Like I said, wallpaper borders. Anywhere there could be a decorative edge, you see these patterns. Both of these have translation symmetry. In this one here, there's different colors involved that may or may not follow that pattern, but if you just look at the figure, that figure has been translated and slid along a line. The second one also has glide reflection symmetry. That means part of it flip-flops. Like here, this is reflected this way. So if there's a reflection, if it flip-flops, then it's got glide reflection, which is when there's a translation and a reflection. So if you're given a frieze pattern, you may assume that the pattern continues forever in both directions. Okay, here's some examples. In A, you have to say whether there's translation symmetry or glide reflection. In A, it's just translation symmetry. It was not reflected at all. It's just that this figure is translated several times. But in this one, you can see that this paw print points this way, and then it's reflected over a line, and now it's down. And there's also this line here. So this one has glide reflection. It also has translation symmetry, but every glide reflection will also have translation symmetry because there's a translation and a reflection going on when you have glide reflection. So on your worksheet, there's a few for you to name with either translation symmetry or glide reflection. All right, a tessellation is a pattern that completely covers a plane with no gaps or overlaps. This is the definition of a tessellation. If you look down at a tile floor, that's an example of a tessellation. Tile floors might have squares that tessellate. They might have rectangles that tessellate. They might have triangles that tessellate. They might even have hexagons or other figures that tessellate. They don't always have to be cute little polygons. If you look at the work of M.C. Escher, he used all kinds of really creative types of tessellations. In this one here, this is a tessellation. It's a quadrilateral that tessellates, and each angle of the quadrilateral occurs once at each vertex. So if you, whatever this angle is, I don't know what it is exactly, but all four of these colors are within this first quadrilateral, and we know that there's 360 degrees if you add up the four angles in a quadrilateral, which means that you put those four angles together and you get this circle that's also 360 degrees. So where the tessellation meets at these vertices is always equal to 360. So if you can figure out if it's 360, then you'll know that it'll tessellate at that plane. Any quadrilateral will. So triangles always add up to 180 degrees, and any triangle can be used to tessellate a plane because you could use 3 triangles and then another 3 triangles to get to the 180. Here's an example of triangles tessellating the plane. So they don't have to be equilateral triangles. And you can see that if there's 6 triangles together, that will equal the 360 degrees that we need in order to tessellate a plane. So some of your questions are going to be asked to say whether or not a figure can tessellate a plane. All right, in this part we're going to copy this figure and use it to create a tessellation. There's a video in your folder that shows how to do this in Sketchpad. But if you're doing this on paper, here's how you'll do it. And there is a problem on the worksheet where you have to do this as well. So here's the triangle. What we're going to do is rotate the triangle 180 degrees about the midpoint of one side. So if you found the midpoint of this side, let's say I found it and it was right there, then I'm going to rotate the triangle about that point, which would give me two triangles together. It looks like they rotated about this point instead. You could rotate about any point though, but they rotated about this point, which created another triangle right here. Next step is to take that pair of triangles, which is now a quadrilateral, and make a row of triangles. So just translate it over and draw that again. And then you can translate that whole row down. They shaded it in so you could see it a little easier. And there you have a tessellation. And you can see you can continue that, translating that figure, and create a larger tessellation if you needed to. All right, in this one, we're going to do the same thing. Pick one side to find the midpoint of. It doesn't matter what side they used this one. And then they rotated the figure 180 degrees about the midpoint to create a rectangle, in this case, or a quadrilateral. And now you can translate that to make a row of them. And then you can translate the row down to make a block of them. This is just another example using the same exact method. So you can see how no matter what figure you start with, if you follow these, if you start with a quadrilateral, you're able to, or a triangle, you can follow these steps in order to create a tessellation. All right, then you need to know that a regular tessellation is formed only by congruent regular polygons. A semi-regular tessellation is formed by two or more different regular polygons. You can have a tessellation that's neither of these, but these are special ones. So here's an example of a regular tessellation. This is made only with equilateral triangles. That's a regular tessellation. This is an example of a semi-regular. It was made with equilateral triangles and squares, both of which are regular polygons. So for these, we're going to say if they're regular, semi-regular, or neither. The first one was created by using, it looks like, trapezoids. Those are not regular figures, so this one is neither. The second one is equilateral triangles, so that one's regular. And the third one, this looks like pattern blocks, doesn't it? We have a hexagon, a square, and a equilateral triangle. So the first one's irregular, it's neither. Second one is a regular, and the last one is a semi-regular because it's created with three different figures. All of them are regular though, so that's called semi-regular. In this part, it's just another example. The first one would be regular because only regular hexagons are used. The second one, I don't know. It looks to me like it could be semi-regular if those are regular hexagons and equilateral triangles, but they say it's neither. I'd have to be able to zoom in closer to see if those are actually regular hexagons and equilateral triangles. The third one looks semi-regular. It has regular hexagons and regular triangles meeting. All right, here we are going to determine whether the given regular polygon can be used to form a tessellation. If so, draw the tessellation. Well, A is going to be yes because it's a triangle, and triangles will tessellate, and it's an equilateral triangle. In B, we're going to look at whether or not we can get to 360. So in a pentagon, and you can Google how many degrees these are in a regular pentagon, but we did find out how to find this. You take the number of sides minus 2 and then multiply that by 180 in order to find how many degrees would be in each well, this is for the sum, sorry. So this would be 180 times, there's 5, so 5 minus 2 is 3. So there's 540 degrees in the whole pentagon, and then you divide by how many angles there are, or how many sides there are, in order to get the 108 in each angle. So take this, divide by n, to find the degrees in an angle. So we have 108 here, and then this is a regular equilateral triangle, so that's 60. So try to figure out if there's some way that you can put 108 and 60 together to get 360. Like, could you add 2 of these and 1 of these, or 2 of these and 1 of these? And you'll find that there's no way to do it. So that means that this is a no. You have to be able to get to 360 in order to use those as a tessellation. All right, if you have any questions, please let me know. Have a wonderful day.